In this section, we will discuss logarithmic functions. To start, let's revisit, let's think back to the previous section where we were discussing exponential functions and think of a few simple exponential functions. Let's, or in this case, not functions, but actually equations. Okay, so we've got 5 raised to the power of x, which equals 5, right? And the variable in this equation is in the exponent there, right? And the solution to this equation is the value of the variable that makes this a true statement, which just by inspection is pretty obvious that the solution is x equals 1, right? Because that will result in the statement 5 equals 5. Similarly, if I have something like 5 raised to the power of x equals 25, just by inspection, it's quite clear that the solution to this equation is x equals 2, right? Because 5 squared is equal to 25. Okay? However, some equations of this format, they're not easily solved just by inspection. Say something like 5 raised to the power of x equals 20, right? It's not obvious what the solution to that equation is. We can say that it's some number between 1 and 2, right? Because 5 raised to the power of 1 is 5. 5 raised to the power of 2 is 25. 20 falls between 5 and 25. But just by inspection, we don't know what the solution to this is. Nor do we really have a tool in our toolbox so far to solve for the variable x, to isolate that variable. So to do that, we need to introduce a new type of function, which we refer to as a logarithmic function. So let's go ahead and look at the official definition of a logarithmic function right here. So a logarithmic function, if x and b are positive real numbers such that b is not equal to 1, then y equals log, and the little subscript there is called the base, so we say log base b of x is called the logarithmic function with base b, right, where log y equals log base b of x is equivalent to b raised to the power of y equals x. Okay, so basically a logarithm is a new function that's defined, and it's an exponent, right? So a logarithmic function always has a base, and the definition of the logarithmic function, it's basically saying we take the base and raise it to the base raised to what power gives me the value of x, right? So the logarithm is defined as the exponent, okay? So we can make a few notes here. Let's see here. Given y equals log base b of x, we could say the value y is the exponent okay, to which b must be raised to obtain x. Okay, so given the function y equals log base b of x, the value y is the exponent to which b must be raised in order to obtain x, right? So we define this new function as the exponent, okay? Some other terminology here. the value of y is called the logarithm. Okay. The value of b is called the base. Okay. And x is called the argument. Okay. So a logarithm has three parts. It has the logarithm, y, the base, which we call b, and x is the argument. Okay. And so the expression y equals log base b of x, okay, and b raised to the power of y equals x, those both define the same relationship. Those are both ways of relating the same quantities between x and y. Y equals log base b of x, that's called the logarithmic form, and b raised to the power of y equals x is called the exponential form, right? So those are two different ways of relating the same three quantities together. So any logarithmic function can be rewritten in exponential form, and then vice versa, any exponential equation can also be written in logarithmic form. Okay, so let's take a look at some examples where we kind of practice that relationship. Okay, in this case, we want to write each equation in exponential form. This first one, log base 4 of 16 equals 2. Remember that 4 is the base, 2 is the exponent, right? And then 16 is the argument. So it would be, in exponential form, would be 4 raised to the power of 2 equals 16, right? We've got the same three numbers, 4, 16, and 2, but we're relating them in a different way. For here, 5 is the base, negative 1 is the exponent. So we have 5 raised to the power of negative 1 equals 0.2. Over here, 8 is the base, 0 is the exponent, right? 8 raised to the power of 0 is equal to 1. 23 is the base, 0 is the exponent, right? 23 raised to the power of 0 is equal to 1, right? We'll look at some other properties of exponents later, but one of the key ones is that the logarithm of 1 is always equal to 0 regardless of what the base is, simply because any number raised to the power of 0 is always equal to 1, right? That's the reason for that. So here we have some exponential expressions, and we want to rewrite these in logarithmic form. Okay, so in this case, 2 is the base, 4 is the exponent, right? 16 is the argument. So we would have log base 2 of 16 is equal, to 4, yeah, equal to the exponent 4, okay? Or here, right, the base is 27, the exponent is 1/3, the argument is 3, right? So we would have log base 27 of 3 is equal to 1/3. or over here, the base is 1/4, the exponent is -2, argument is 16, right? So we would have log base 1/4 of 16 is equal to -2. Okay, so hopefully with some practice you start to see how those three quantities can be related either in the exponential way or the logarithmic form. Okay. Now let's say we want to just practice evaluating some logarithmic expressions, right? Evaluate log base 12 of 144, right? So we would say 12 raised to what power is equal to 144? Or if you want to, we could say, the exponent is the unknown quantity, so we could express this in exponential form as 12 raised to some unknown quantity, x, equals 144. And if you relate it that way, then by inspection, we should be able to say that x equals 2, right? Because 12 squared is equal to 144. Similarly, over here, we would say 64 raised to what power is equal to 8, right? Or we could say 64 raised to the power of the unknown quantity x is equal to 8. In this case, x is equal to 1/2. Raising a number to the power of 1/2 is the same thing as taking the square root of that number, right? And the square root of 64 is equal to 8. So that's why it's that result, right? Or over here, right, 3 raised to what power equals 27. We could say 3 raised to the power of x equals 1/27. This one may not be quite as obvious just by looking at it, but if we rearrange it a little bit, it becomes more obvious. We could say 3 raised to the power of x equals 1/3 cubed, because 3 cubed is equal to 27. And then I could write that as 3 raised to the power of x equals 3 raised to the power of -3, because that's just a property of fractions, right? I can bring this to the top and change the sign of the exponent. And then one of the basic rules of exponentials is that if you have two exponential expressions with the same base, then the only way that could be true is if the exponents are equal, right? So that means that x has to equal -3 in this one. Okay. So that's how logarithmic expressions work. Now, these examples that we looked at, they're relatively straightforward to work out, just kind of by hand or by inspection. Not every logarithmic expression is that easy. I think I had right at the very beginning of this section, I put up on the screen the expression 5 raised to the power of x equals 20, right? I could rewrite that in logarithmic form if I want to. Log base 5 of 20 equals the unknown value x, right? But evaluating the expression log base 5 of 20, it's not easy, right? We don't really have a inspection or a by hand way of doing that. Now, most calculators, at least more advanced calculators, might have the ability to do that. Or there's certainly technological tools that can, right? So that's what you would rely on for evaluating something like that. Later in the class, we'll look at some tools that allow us to take a logarithmic expression like that and turn it into something that's easier to evaluate on a calculator. But for now, I just want to introduce two types of logarithmic functions that are more commonly used than most of them. These are the kind of the two most commonly used logarithmic functions in most applications, in a lot of applications. There's the common logarithmic function, which is simply a logarithm with a base of 10, and then the natural logarithmic function, which is a logarithm with a base of e, a special number e, which we introduced in the previous section, that's used in a lot of applications involving exponential functions. It's also used in logarithms. So because these two types of logarithms are used so frequently, then we have some special symbols or notation to represent these. So a common logarithm is often expressed as just log. The base is not written in, right? So if the base is not written in, it's just assumed to be 10. That's a common logarithmic function. And then a natural logarithmic function, we typically use the symbol ln to represent that. So if you see ln of x, that's just a logarithm with a base of e. Now because common logarithms and natural logarithms are so commonly used, every scientific calculator will have a key or a button or a method of just evaluating these. And it might look different for different calculators, but if you have yours, you should just look at your calculator and you should find a way of how to do it on yours. It might just be a special key, or it might be a secondary command where you have to press the shift and then another key. But you should see somewhere on your calculator, you should see a log x and an ln x. And if you have any questions about that, feel free to reach out to me. And I can probably help you with that as well. But yeah, these are two of the most important logarithms. And like I said, so scientific calculators will have the ability just to compute those for any argument x, as long as it's defined for that argument. Okay, so let's go over a few examples. Okay. And these ones can be evaluated without the need of a calculator. Log 100, right? So because the base is not written in there, then it's just assumed to be 10. That's a common logarithm, right? So we would say 10 raised to what power equals 100, right? 10 raised to what power equals 100? And the answer would be 2, right? Because 10 squared equals 100. So log 100 is equal to 2. Over here, log 0.0001, right? Again, no base is written in, so it's assumed to be 10, right? So we could say 10 raised to what power equals 0.0001, right? This is this is basically the answer here would be -4, right? Because 10 raised to the power of -4, that would be the same thing as 1 over 10 to the 4th power, and that would give you 0.0001 if you did that. Okay. ln of e raised to the power of -3. We would say e raised to what power gives me e to the -3. Clearly, that would just be -3, right? In this case, the argument of the logarithm is an exponential with a base that's the same as the logarithm itself, right? And so the answer to that will just be the exponent. Similar thing here, right? ln e to the 10. We would say, so it's a logarithm with a base of e. E raised to what power will result in e raised to the power of 10? Well, clearly, that will just be 10, right? E raised to the power of 10 is equal to the argument e raised to the power of 10. Okay. Now, some logarithms, like we said, are not so straightforward to evaluate just by inspection or by hand, right? Something like log 43, right? That we would say 10 raised to what power equals 43. It's not obvious what that is, but you can use the log key on your calculator to evaluate that. If you have your calculator handy, this would be a good time to practice that, just getting familiar with that, right? If you plug this into your calculator, you'll get you'll get a number that kind of is an irrational number, right, that keeps repeating an infinite number of decimal values. But if we round it down to about 4 decimal places, we'd get 1.6335. And then we could check that by taking 10 and raising it to the power of 1.6335, and we get a number that's very close to 43, right? So it checks out. Because it's not exactly 43, that's just because we rounded this number off, right? So, these other ones, you would use your calculator to evaluate. Log 200, we would say 10 raised to what power is equal to 200. It's not obvious what that is, but you could use the log key on your calculator, and you would find that to be approximately 2.301. Okay? Log 0.074. 10 raised to what power is equal to 0.074. Not obvious what that is, but your calculator would tell you that's equal to about negative 1.1308. Okay? Again, I would have your calculator verify these numbers. Okay? ln 200. That would be saying take a base of e raised to what power is equal to 200, right? Not obvious what that is, but you could use the ln key on your calculator and evaluate this and get about 5.2983. Okay? So that means that e raised to the power of 5.2983 is approximately equal to 200. That's actually about 199.9965. Okay. Again, the fact that it's not exactly equal to 200 is because we have to round this down to 4 decimal places, right? ln 1.005. E raised to what power results in 1.005. Not obvious what that is, but if you plug it into your calculator, you would get about 0.005 as that result. Okay. So those keys on your calculator can be really handy for helping with logarithmic expressions. Okay, let's go over just some basic properties of logarithms, and most of these properties exist because of certain other properties of exponentials. Okay. For example, the logarithm of 1 is always equal to 0. The reason for that is because any number raised to the power of 0 is always equal to 1, right? So those are related to each other. So it does not matter what the base is. If the argument is 1, the result is 0. Log base b of b is equal to 1, right? So if the argument of the logarithm is the same number as the base, the result is just equal to 1. And that's simply because if you take a base of b, you would be saying, b raised to what power equals b? Well, clearly, b raised to the power of 1 equals b, right? So that's why the logarithm of the base is equal to 1. Log base b of b to the x is equal to x, right? We looked at a couple of natural logarithms that were similar to this, right? And that's just simply because b raised to the power of x is equal to the argument, which is b raised to the power of x, right? So this is the corresponding exponential form, right? That's why that's the case. B raised to the power of log base b of x is equal to x, right? So if the exponent is a logarithm with the same base as the exponential, right, the result is x. And that's because if you rewrote this in logarithmic form, right, we would get log base b of x is equal to the exponent, which is log base b of x, right? If you rewrote this in logarithmic form, you would just get this statement, which is a always true statement, right? So these are properties of logarithms that always hold true because of certain other properties of exponentials, right? If I were to apply some of these expressions, log 19 of 19 Well, this is equal to 1, right, because of this property, because the base and the argument are the same number. Log 10, well, this is equal to 1 as well, because the base is not written in, it's assumed to be 10, right? So this is log base 10 of 10. ln(e), well, this is also equal to 1 because ln is a natural logarithm. It's a logarithm with a base of e, right? So log base e of e is equal to 1 because of this property right here. Log base 273 of 1 is equal to 0 because the logarithm of 1 is always 0 regardless of what the base is, right? Same here, 0. Log base 30 of 30 raised to the power of 10, this is just going to be equal to 10 because of this property right here, right? Because the argument is an exponential with a base that's the same as the logarithm. So the result is just going to be the exponent of that. Okay? Okay, let's now explore graphing. Let's say we have the expression y equals log base 3 of x, and we want to graph it, right? So graphing previous functions, what we've typically done is we have chosen some x values, plugged those in and solved for y, plotted those points, and then sketched the graph. With a logarithmic function, actually the easiest way to graph it is to start by rewriting it in exponential form, right? So if my function is y equals log base 3 of x, in exponential form, that would be a base of 3 raised to the power of y is equal to x, right? So that is the way of relating the x and the y values in the exponential form. And then, using this form, what we do is we choose y values first and solve for x, right? So it's a little bit different from how we've done it previously, right? So I would start by choosing y values and then plug those in and solve for x. So like, for example, I might choose y equals 0. 3 raised to the power of 0 equals 1. So that would be the x value. Might choose y equals 1. 3 raised to the power of 1 equals x, which would be 3, right? This would result in 3 squared, so x equals 9. Okay? Do 3. 3 cubed is equal to 27. And then a few negative exponents, perhaps. So something like -1. All right, so 3 raised to the power of -1 equals 1/3. Maybe -2. 3 raised to the power of -2 equals 1/9. -3. 3 raised to the power of -3 equals 1/27. And then we would just graph these ordered pairs. And actually the graph is already here for us, but the point 1, 0 is right there. 3, 1 is right there. 9, 2 is right here. 27, 3 is up here. Okay. 1/3, -1 is right here. 1/9, -2 is right here. And 1/27, -3 is right here. And so we sketch the graph like this. Okay? And what we observe is this is kind of a typical logarithmic function graph. What we observe is that it's increasing everywhere, right? But as x increases, the graph gets less and less steep, right? So it's decreasing at it's increasing at a slower and slower rate. Also, the y-axis serves as a horizontal asymptote, right? It approaches the y-axis but never quite touches it. So one thing that we observe with this is that the y value, or when you can basically, the result of a logarithmic expression will never be a negative number. I'm sorry, the x value, it's only, basically the function is only defined for positive x values, right? Because the entire graph sits to the right of the y-axis, right? Only for positive x values. So if you try to evaluate a logarithm for a negative x value, it's undefined, okay? It's only defined for positive x values, as you can see here. And it's worth comparing a typical logarithmic function graph with that of a typical exponential function graph. Essentially, a logarithmic function is an inverse function of an exponential function. We went over inverse functions a few sections ago, right? And so if you graph these, one of the properties that when you graph a function and its inverse, the two graphs will exhibit a certain symmetry. The line of symmetry is the line y equals x, which just passes right through here. Okay, you can see that the two graphs are a reflection. And they exhibit a lot of kind of opposite properties, right? The blue represents the graph of a typical exponential function. The red represents the graph of a typical logarithmic function. For the exponential function, the domain is all real numbers, right? It's defined for any x value. You can plug any x value you want into that. But the range is defined for only positive numbers. The range would be y values. You'll notice that the entire graph sits above the x-axis, right? So it's only for y. So the range is only y values, but the domain could be any number. For the exponential function, the horizontal axis, or the x-axis, serves as a horizontal asymptote, and it always passes through the point 0, 1, simply because anything raised to the power of 0 is equal to 1. For the logarithmic function, we see some kind of opposite behavior. The range is all real numbers, but the domain is restricted to positive numbers only, right? Because the entire graph sits to the right of the y-axis. The y-axis serves as a vertical asymptote, and it passes through the point 1, 0. Okay? So a lot of these properties are basically the opposite for the logarithmic expression, kind of illustrating that inverse relationship between a logarithmic function and an exponential function. And finally, just to kind of wrap up this section, we're going to work out one problem that illustrates a typical application of logarithmic functions. Logarithms are used a lot in kind of scientific applications, especially cases where we have numbers that are measured on a huge scale. And the logarithmic scale kind of makes the numbers more manageable. An astronomy example is measuring the brightness of stars. We refer to the brightness as the magnitude. But there's two ways of interpreting a magnitude. There's the absolute magnitude of a star, which we use capital M to refer to that, and the apparent magnitude of a star, which is lowercase m. The apparent magnitude, the absolute magnitude is the apparent magnitude a star would have if it were placed 10 parsecs from the Earth. Okay? A parsec is a measure of distance used in astronomy for measuring very large distances. Okay? So, like, for example, our sun is a star, right? And our sun appears brighter than all the other stars that we observe in the night sky, right? The sun is so bright that during the daytime we can't even see any of the other stars because the light from the sun drowns them out. However, that doesn't mean that our sun is actually the brightest star out there. The reason our sun appears so much brighter is because it's so much closer to us, right? The other stars are much, much, much farther away, right? Which is really why they appear so much dimmer. So that's why the absolute magnitude is basically saying if all the stars were at the same distance, right? It would be kind of fixing the distance and saying what would the brightness be if the distance were fixed, right? If all the stars were the same distance away from us, then we would see that some of the stars in the night sky that appear dim would actually be brighter than our sun if they were at the same distance away from us at the sun, right? So that's this idea of absolute versus apparent. Apparent is the observed brightness, right? Our observed brightness is that our sun is brighter, right? Absolute would be kind of, the fixed magnitude of the stars if they were at a fixed distance from us. The way the magnitude measurements work, the smaller the number, the brighter the star. And so a negative magnitude really corresponds to something that's quite bright. Our sun has an apparent magnitude of negative 26.74. The brightest star in our night sky is Sirius, the dog star, with an apparent magnitude of negative 1.44, right? The sun appears so bright because it's very close. So this formula here, involving a logarithm, relates a star's absolute magnitude, apparent magnitude, and its distance from Earth in parsecs. So the question is, if Sirius is 2.637 parsecs from Earth, and the sun is 4.887 times 10 to the minus 6 parsecs from Earth, what is the absolute magnitude of each star? Okay. So let's start by finding the absolute magnitude of Sirius, okay, using this formula. Let's do Sirius. Okay, with Sirius, we have the apparent magnitude, m, is equal to negative 1.44. Distance is equal to 2.637 parsecs. So the absolute magnitude, m, is equal to negative 1.44 minus 5 times log 2.637 divided by 10, which is approximately equal to 1.45. Okay, so this you could evaluate relatively easily on your calculator using the log button. You would just, do log, and then you would literally type in 2.637 divided by 10. Then you would multiply that resulting number by 5 and subtract it from negative 1.44. Okay? For our sun, we're told that the apparent magnitude is negative 26.74. Okay. The distance is 4.887 times 10 to the minus 6, right? That would be basically the 10 to the minus 6 simply means take the decimal point and move it 6 places to the left, right? 0.00004887. This is using what we call scientific notation, kind of a shorthand for making the numbers more manageable. So the absolute magnitude is equal to negative 26.74 minus 5 times log 4.887 times 10 to the minus 6 over 10. And evaluating that on your calculator, you get about 4.81. Okay. So if Sirius and the sun were a fixed distance from us, a distance of exactly 10 parsecs, Sirius would have a magnitude of 1.45. The sun would have a magnitude of 4.81. And remember, a smaller number corresponds to a brighter star. So Sirius would be the brighter star if they were at a fixed distance. And the way logarithmic scales work, even though 1.45 doesn't look substantially lower than 4.81, like 3.4, something like that, but that a small difference corresponds to a huge amount, right? So Sirius would actually be multiple times brighter than the sun at a fixed distance. So yeah, so the only reason the sun looks so much brighter is because it's so much closer, right? But Sirius, in reality, is actually a much brighter star. So that's kind of a typical example of where a logarithmic equation might work. Logarithms are also used in things like measuring the intensity of earthquakes. And there's numerous other examples in the sciences where logarithms come in really handy. But for today, we will wrap it up here. So thank you for watching.